In the early days, the rapid growth in electrical energy use and the demand for low-cost energy drove the development of generation sites situated far from the load centers. These remote generating stations varied in type, ranging from hydroelectric stations requiring sites with high heads and significant water flows to fossil fuel stations located near coal mines. Even geothermal stations, tidal power plants, and nuclear power plants had to be site-bound or purposely built distant from urban centers. As you can imagine, generating bulk power at these remote locations necessitated the use of transmission lines to connect these generation sites to load centers. To enhance system reliability, multiple lines were used to connect load centers to several sources. Neighboring utilities were interlinked and necessary levels of redundancy were provided. This interconnectedness made the electrical transmission network quite complex. A typical electrical power transmission network comprises mostly three-phase alternating current, or AC, transmission lines operating at different transmission voltages, generally at 230 kilovolts and higher. As the requirement for power transmission capacity increased, or when longer transmission distances were needed, these transmission voltages continued to increase. In fact, increases in transmission voltages are closely linked to decreasing transmission losses. Over time, transmission voltages gradually increased to 765 kilovolts, with power transmission reaching 1500 MVA. An AC power transmission network primarily consists of three-phase overhead lines. These are cheaper to build and maintain but require expensive rights-of-way. In densely populated areas where these costs are very high, underground cable transmission is used. From an ecological and aesthetic viewpoint and for improved reliability, underground transmission is preferred for future expansion. In a complex interconnected AC transmission network, the source to a load power flow finds multiple transmission paths. A load flow study must be performed to determine the levels of active and reactive power flows on all lines. The flow of active and reactive powers on a line is determined by its impedance and the voltages at its terminals. Despite the reliability of interconnected AC transmission networks, there is no control over line loading. However, series and/or shunt circuit elements such as capacitors and reactors can be added to modify loading capacity. The long-distance separation of a generating station from a load center requires long transmission lines of high capacity. The use of AC-DC and DC-AC converters at the terminals of an HVDC line offers a viable alternative. Currently, HVDC transmission has grown up to plus 600 kilovolts with about 4,000 A capacity. The most significant feature of an HVDC transmission network is its full controllability on power transmission. Recently, active and reactive power in AC transmission networks is adjusted by modifying transmission line impedances, regulating terminal voltages by generator excitation control, and transformer tap changers. Series and shunt impedances are also employed to effectively change line impedances. In summary, the development of electrical energy generation and transmission has been a journey of innovation and adaptation, driven by the need for system reliability, control, and increasing demands. The future promises even more exciting developments as we strive for more efficient and sustainable methods of electrical energy generation and transmission.